But invariant measures, right? Remember that we have some kind of metric space, some map, and mu probability measure is invariant if mu of minus 1 of A equals mu of A, okay? For all A in the sigma algebra that we've considered. So we looked at some examples of invariant measures last time. Now we're going to prove the Krylov-Bogulyubov theorem that says that if you have a continuous map on a compact metric space, that always exists. And the theorem is not so difficult, but it's an opportunity to introduce some ideas and some tools and some notions related to invariant measures. So one of them is the space let's call MF equals the space of all mu F invariant measures. Okay, so we don't know what this space is a priori. So do you know what the weak star topology is on the space of measures? So do you know that measures can be thought of as linear functionals on the space of continuous functions? Have you all done that? No? No, you've not done it yet. Okay. So, I think you will probably do it in the analysis course, I imagine, in the function analysis course that you've got this semester. But I'll just briefly mention that if you have, if phi is a continuous function, so if, let's take the C0 continuous functions from x to r is equal to all the functions phi from x to r, which are continuous, okay? Then, and mu is a probability measure, not necessarily an invariant one, right? So mu probability measure, then we can define a map mu from C0 xr to r, which assigns to every function the integral of phi d mu. So the measure, so you've done the integrals, Lebesgue integration, right? Yes. So you know what the integral with respect to the measure means. Yes? Or do I need to remind you about that? Okay? Okay. So one way to see measures is as linear functional. So this is a functional because it's a space of it's a measure from it goes from the space of continuous functions to R. This is a linear functional. It's linear. It's easy to check that it's linear if you take phi plus psi. That gives you the integral of phi plus the integral of psi. So linear functional. So the space of all measures is the space of all linear functions. Okay, there's some results from function analysis that describe this, and you can identify every measure produces a linear functional, and every linear functional defines a measure, because the measure can be defined through the linear functional. So the space of linear functional and the space of continuous function is exactly the space of measures. Okay? The space of probability measures is just a space of continuous functions for which this integral is equal to 1, because that's the measure of the whole space. And we use this to define a topology on the space of measures, which is the topology on the space of linear functionals. But I'm not sure how familiar all this stuff is for you. So we can define the weak star topology. It's called a weak star topology on M. So we can define it on M or on MF, and we can start topology on F. Is the following. So one way to define a topology is to define what it means for a sequence to converge. Okay? So we say that mu n, sequence mu n converges to mu if the integral of phi d mu n converges to the integral of phi d mu for all continuous functions. This is called weak star because this is the topology, the natural topology on the dual space. So the space of linear functions is sometimes called the dual space. We will not use any of this terminology specifically, okay? And I'm sure you will cover it in more detail in the function analysis course. But we will use this definition of this topology because it is relevant and it's very important. But so the space of linear functions on a Banach space is called the dual of that space, okay? And on the dual, which is the space of linear functions, there's a natural topology called the weak star topology, which is defined exactly by this, right? Which is defined by saying that this converges to this as linear functionals in some sense, so that this should be d mu n, yes. D mu n converges to integral of phi d mu. Okay, so this is called the weak star topology. We will see some applications of this in some examples. It's actually fairly easy to apply this.
So here you use a word weak. In which sense this is weak or strong?
Excuse me?
Here I use a weak. So in which sense this is a weak or strong? Any difference? Or
this is called weak star because it is the name that is used for the topology on the dual space. It's a weak topology on the dual space because the convergence is a kind of weak convergence in this dual space, because in infinite dimensional Banach spaces you have several different kinds of convergence, right? Several different topologies.
Yeah, but like in topology we use the word weak is the weakest topology or some sense in a point-wise convergence.
No, don't think about it like that. This is just a specific name that you don't need to worry about what it means. This is the definition of it. Okay, just think about that. It's just called weak star topology because it comes from some terminology that's used in function analysis to define these topologies on the dual spaces of certain Banach spaces. Okay, so that's just a name. But what we will use is this definition. This is important and we will use it, but it's actually really not very difficult to use, as we shall see. So one comment, again, I'm just doing a general recap from functional analysis, is that if X is compact, which is our space here, okay, then the space of I didn't define it, but let me define M is equal to just the space of probability measures on X, not necessarily invariant, probability measures on X is compact in the weak star topology. Okay, this is a fact from functional analysis. So the space of invariant measures is a subset of the space of probability measures, and we're going to use this topology to show that there exist some invariant measures. I will explain how we're going to do that. Let me make one more remark. Also, as a general fact, the space of, notice that MF is a subset of M, of course. Okay. In principle, it may be empty, a priori. We're going to show that it's non-empty if X is compact and F is continuous. That's the theorem we want to prove. Let me also notice also that M is also a kind of a convex space, right? Because the sum, you can take the linear combination of two measures is also a measure, and even if they're invariant, so MF is convex, okay, i.e. in the sense that if mu1 and mu2 are invariant measures, and then for all t in 0, 1, we have that the measure mu t is equal to t mu1 plus 1 minus t mu2 is also an invariant measure. This you can check as an exercise. It's very easy to check. Okay. Exercise. So this is true, of course, just for measures. If you have two measures, you take any linear combinations of measures, it's a measure. If you take probability measures and you take linear combination of this kind, then it's also a probability measure. But in particular, if the two measures are invariant, then this linear combination is also invariant. Okay? So the first observation that I've not stated in the theorem is that if X is compact, then the set of invariant measures, which is a set that we'll be working on, is convex and compact. Sorry, the space of measures is compact, and the space of invariant measures is convex. Yes. In fact, we will show it's also true that the space of invariant measures is compact, but I cannot remember if I included a proof here. Maybe I left it as an exercise. Okay. Anyway, the thing that we're most interested in is the fact that this is non-empty. And this is what we're going to prove. So first we're going to introduce, again, now that we have this notation, we're going to introduce a map on the space of measures. So we define a map. Define a map F, which we call F star, which is from the space of measures on our space X to the space of measures, and it's defined like this by F star mu over set A is by definition equals to mu of F minus 1 over F. For all A in the Borel sigma algebra. So I will leave it again as an exercise to check that this is well defined. So check that F star of mu is indeed a measure. Okay? So intuitively the definition is fairly easy. We have our space, we have our map, and then we look at each set A. Okay, we say what's the measure of A? Well, it has a certain measure by mu, but now we're going to define a new measure of A by looking at the pre-image of A. Okay, this is F minus 1 of A. Looking at the measure of F minus 1 of A, and that value is what we assign to be the measure of A. Okay, so this is important because we are introducing the dynamics as a way to construct the sequence of measures. We will iterate this map. This is called the push-forward map. or f star is called a pullback. F star is sometimes called a pullback of mu, of the measure mu. F star of mu is called a pullback. This is the pullback map. And notice that what happens if f star of mu equals mu, then it's invariant, right? Because by definition, if f star of mu equals mu, then this implies that mu of A is equal to mu of f minus 1 of A, which is the definition of invariance, okay? So so it's a fixed point for this f star. So being invariant, f star, okay, this if and only if mu is invariant. So the invariant measures correspond exactly to the fixed points of this push forward map. Okay? So this is what we're going to use to show that the set of invariant measures is invariant. In some sense, we're going to show that there exist fixed points, although we're not going to show it by a fixed point argument. We're going to show it dynamically. You can't really just apply a kind of one of the standard fixed point arguments, because this is not a contraction or anything like that. We cannot show that this is a contraction on the space, besides the fact that we have a topology, we don't really have a metric. Anyway, this is still what we're going to get. Okay? So the way we do this is we're going to iterate this map and show that in fact, if you take a measure and you iterate it by the pullback, lots of times you converge to a fixed point. Okay, this is going to be a strategy. It's quite dynamical argument. So the first lemma that we need for this this is called, I always get confused actually. In the notes I have it push forward. So every mathematician I know never remembers what you call push forward and what you call pullback. Okay? And because in some ways you are, I guess you're pushing forward the measure in the sense that you're taking the pre-image and you're taking the value of the measure here and you're in some sense pushing it forward to here. Okay? So I guess this is really not the pullback, but often people will call it pullback because you're kind of pulling back the set. It's not a standard terminology necessarily. So, okay, so the first lemma, the crucial lemma here, is that for all phi in L1 of some measure mu, we have that the integral of phi composed with the push forward measure mu is given exactly by the integral of phi composed with f d mu. Which is actually, when you think about what it says, it's fairly intuitive. And so the easiest way to see it is with the, suppose first of all that phi is the characteristic function of some set A. Okay, then what does this mean? So here we have our map, here we have our set A, here we have the pre-image of A, and then we have, so what is f star? So the integral of phi df star mu is equal to the integral of the characteristic function of A with respect to the measure f star mu. And you know what the integral of characteristic function is, right? is just equal to the measure of A. Okay? The Lebesgue integral of a characteristic function is the measure. So by definition, this is equal to mu of f minus 1 of A. Right? And we can write this as the integral of the characteristic function of f minus 1 of A d mu. Okay? And what is the characteristic function of f minus 1 of A? This takes value 1 for every point whose pre-image is in A. So this is exactly equal to the characteristic function of A composed with f d mu. Right? Because you take all the points. If a point belongs to f minus 1 of A, it means its image belongs to A. So this function here is 1 exactly when this function here is 1. Right? You take a point, you apply f, and it belongs to A. It's the same thing as belonging to f minus 1. So this is exactly this statement, and this is equal to integral phi composed with f. Right? So this is easy in the case of characteristic functions. And then actually these I will go through briefly, but this is in real maybe you've done in real analysis. There's very standard approximation arguments where if you can prove something for characteristic functions, then you can prove things for all L1 functions. I'll just sketch the steps, but basically this is the key point, and then you prove it for L1 functions because you just approximate L1 functions by combinations of characteristic functions. So clearly this holds also for simple functions. You know what simple functions are? Simple functions are just finite sums of characteristic functions. Okay? So simple functions which is a linear combination. So linear combinations of characteristic functions. Just by exactly the same argument, right? You just take a linear combination. Then, if phi is a non-negative integrable function, so let phi greater than or equal to 0 in L1, then it is a pointwise limit of a sequence of simple functions. Of a sequence of simple functions. This is also a basic fact from analysis that this is the case, right? And therefore simple functions phi n, let me write phi n, and which can be taken increasing, because this is non-negative, so we can be taken of simple increasing functions. So sorry, the sequence is increasing. Pointwise limit of an increasing, in the sense that phi n plus 1 is larger than or equal to phi n at every step. And then, so then also phi n composed with f is also increasing and converging to phi composed with F. Okay, so this is the key point. This is the way we approximate both phi and phi composed with F. So suppose first that phi is greater than or equal to 0, then you can take it as a limit of simple functions for which we have this, right? Pointwise limit, and then it's easy to see that this is also an increasing an increasing sequence of simple functions that converges to phi composed with F. Okay, and then we have so by the definition of Lebesgue integral, so because these are simple functions, the definition of Lebesgue integral is basically that the integral is the limit of the integrals of the simple functions, right? So we have that integral of phi n, integral of phi n d f star mu converges to the integral of phi df star mu, and the integral of phi n composed with f d mu converges to the integral of phi composed with f d mu. Okay, this is just because this phi is the pointwise limit of increasing sequence phi n. Phi composed with f is the limit of increasing sequence phi n composed with f. But here these are simple functions, right? So these are simple functions, and for this we just proved that this is equal to this, right? And therefore the limits must be the same. Okay? And then, as usual, this is for positive. If it's not positive, you separate the positive and the negative real part, and you do each argument for the positive and the negative real part separately. Okay, so this has two corollaries which we will use. Corollary 1, which says that f star from m to m is continuous. So on m we have the weak star topology, so we can define the notion of continuity. And why is it continuous? So suppose, how do we show that it's continuous? So suppose we have a sequence converging to mu, right? To show that it's continuous, we just need to show that f star of mu n converges to f star of mu. That's the continuity, right? Then for all phi continuous, we have that the integral of phi with respect to d f star mu n, which is equal to the integral by the lemma is equal to the integral of phi, composed with f d mu n So this is a continuous function. This is also a continuous function when f is continuous. Sorry, I should have said this is now assuming that. So this part here does not use the fact that f is continuous. Okay, I don't think it uses the fact that f is continuous. But here we show that if f from x to x is continuous, okay, then f star is continuous. Otherwise it could not be true. So this is also a continuous function. So by definition of the fact that mu n converges to mu, by the definition of this convergence, says that this converges to phi composed with f d mu, right? And then we apply that again, and we get that this is equal to integral of phi df star mu. Okay, so now we have that for any continuous function, the integral of phi with respect to the sequence f star mu n converges to the integral of phi with respect to df star mu, which is exactly the definition of weak star convergence, which shows that the sequence fs star and mu, right? So f star mu n converges to f star mu. In the weak star topology, and therefore this shows that this is continuous.
So, if here is
F star is continuous. So I'm trying to show that F star is continuous as a map from this topological space, from this space to itself as a topological space, if little f is continuous. And we use that lemma as an immediate consequence. We take a converging sequence, and the definition of continuity, by definition of continuity, f star is continuous if for any converging subsequence here, the image of this point converges to the image of this, right? So fn, we need to show that fn star n of mu n converges to f star of mu. Okay? And so using this lemma, we convert, in both cases, we convert the integrals of phi with respect to d star mu n to integrals with respect to mu n, and therefore we have the convergence here by this, right? This is what gives this convergence here, and therefore this gives the convergence of this to this, which gives the continuity. Okay?
So where we use the continuity of f?
Good question. To say that this is continuous, because this is the composition of two continuous functions.
Yes.
Well, it's this is a map from x to x, but if this is continuous, then this composition will be itself a continuous function from x to r, right? When we say here phi continuous, we mean phi from x to r, right? The weak star topology says that for every continuous function from x to r, then you have the convergence of these integrals here, right? So for every continuous function, so in particular phi composed with f is also a continuous function from x to r. So because we have assumed that mu n is converging to mu, then it means that by definition of this convergence, we have this converging to this for this particular continuous function, right? And therefore this means that this converges to this, which implies this. And the second corollary which we will use is a characterization of when f star is invariant. So corollary 2 is that mu is invariant, mu is f invariant if and only if integral of phi composed with f. The mu is actually equal to integral of phi to mu, or phi continuous. This is almost obvious, but at least one direction is a trivial consequence of this, right? So proof: if mu is invariant, then if mu is invariant, then we have that f star of mu remember that mu is invariant if and only if f star of mu equals mu. Right? So that's what it gives. So if f is invariant, then you have by this lemma here that phi of df star of mu is equal to phi d mu, which is equal to phi composed with f d mu. So you get this. Okay? So this implies, okay, this implies this part here. Composed with f d mu is equal to the rate phi d mu. Okay, conversely, we simply have that if you take the integral of phi d mu is equal to equal to the integral of phi composed with f d mu. So we assume that this is true, right? So we write phi d mu equals phi composed with f d mu, and then we use the lemma to say that this is equal to the integral of phi df star mu. Yeah?
Take phi to be the characteristic.
Well, what we need to show now is that this implies that these two measures are the same, right? And so this is true for all phi continuous, and this is again really basically again goes to a theorem of functional analysis that if these measures are linear functionals and if linear functionals coincide on every continuous functions, then they're the same linear functionals, so they're the same measure. So this uses a little bit of a theorem in functional analysis, which is very, so by, this is the least representation theorem. So by least representation theorem, if a linear functional, so the measures, since the measures, how shall we say, the measures mu and f star of mu, seen as linear functionals, take the same values, on all continuous functions. And so mu is equal to f star.
This is hand-Banach theorem or least representation?
But the least representation theorem says that every measure can be seen as a linear function. That the space of measures,
That every measure has a representation.
That every measure has a representation as a linear function.
In the L1 functions.
Sorry?
In the L1 functions, uniquely. So,
The other way, right? The other.
That's right. So
Every linear function has a representation as a measure.
right.
That's the goal.
Right.
and it's unique.
Yes. So there's an identification between the space of measures and the space of linear functions, between the measures and the linear functions. Yes. So you're right. So in principle, these are linear functionals. Yes. So every L1 function. So how does it go? So yes, you're right, because the invariance. Okay, sorry, you're right. So what we need to show, so we have this equality for all continuous functions, but we need to show that we have this equality for all L1 functions, right? Because that's what the invariance means. So the invariance is that invariance, the definition of invariance says that, sorry, what do I want to write here? So the definition of invariance.
We don't need it for L1 functions. We just need it for the characteristic of a set. Yeah, it's not continuous, okay. It can be approximated by continuous functions.
Which is basically what we're saying here.
Yes.
Yes. Yes. So we check it for continuous functions, and then that extends, and therefore the two measures are the same. It's enough that they coincide on continuous functions. Okay, so now we are ready. We're basically going to use these two corollaries, the fact that f star is continuous and this characterization of invariant measures. And we're going to now use the push forward to construct our invariant measure. So we have, let me write down the theorem again. So theorem, if x is compact and fx is continuous, okay, then the space of invariant measures is non-empty. This is what we want to show. So let mu0 be an arbitrary measure in M. So remember, M is the space of all probability measures. How do we know that this space is non-empty? The space of all probability measures on this space. Sorry? Yes, you can always take the Dirac delta on one point of x. Right? So as long as x is non-empty, there is at least one probability measure. Right? So in fact, you can think of this as the Dirac delta on a point. It's also a good way to think about it. And then for all n greater than equal to 1, we define this sequence of measures, which is mu n is equal to 1 over n, the sum of f star I equals 0 to n minus 1 of mu. Okay, so fi star of mu is just a push forward. So fi star of mu of a set A is just equal to mu of f minus I of A. Right? So it's just the iterates of the push forward map that we had before. So what we're doing is we are kind of using the dynamics. So we have our set A, right? And we're going to define mu n of A by looking at the pre-image f minus I of A. And then we're taking the averages of these, right? So you define a measure of the set A, and you define all these pre-images, and you define a sequence of measures on the set A, which is given by the measure of the pre-image. So this is going to be crucial, is the fact that we're using the dynamics. So this is a dynamical construction of a sequence of measures, right? And so it's somehow, in a way which is not perhaps immediately clear, these measures contain information about the dynamics, because they tell you, they contain information about how the pre-images of sets kind of distribute themselves in space. So it's easy to check that mu n is a probability measure, right? Mu n is a probability measure in the sense that the measure of the whole space is 1, right? Because each of these is a probability measure. If you take f star mu of the whole space, it's mu of the pre-image of the whole space, which is the whole space. So the measure of the whole space of each of these is 1. There's n copies, so this is a probability space, right? It's just a combination of probability measures. And M is compact. So since M is compact, in the weak star topology, as we said at the beginning, M is compact in weak star, then this sequence has some accumulation points. Okay? Then there exists a converging subsequence. Converging subsequence mu. So mu and j converging to mu. There exists converging subsequence. So there exists mu and a converging subsequence mu and j converging to mu.
I think you mean there
Sorry,
in the first equation mu 0. Mu n equals to at the end. The first equation, the definition of the sequence.
Yeah.
I think you mean at the end mu 0.
Sorry, yes, of course. Yes.
Why is mu compact in the weak star?
This is because if X is compact, then the space of probability measures on X is compact. This is again to do with the functional analytic results about the compactness in the weak star topology of the linear functionals on the space of continuous functions in a compact space. It's a fact from functional analysis. It's the unit ball, because the probability measures, so it's the unit ball of the dual of the space. It's compact. This is by some theorem that I cannot remember what's the name. Okay, so we're going to show that every accumulation point is invariant. Okay, simple as that. So we have, by compactness, we have accumulation points, and every accumulation point is invariant. And so we're just going to use the fact that we have an accumulation point, and let's check. So we show that mu belongs to NF, so it's invariant. So how do you show this invariant? We just slide, this is just a kind of one line, slide along the line, but F star of mu and j. So to show that it's invariant, we need to show, i.e., that F star mu is equal to mu. Okay? And to do this, we will show that this follows from the fact that F star n of mu and j converges to, what are we going to show that it converges to? That it converges to mu. So, well, let me say this one after we've done this calculation. So let's calculate F star of mu and j. So we take F star here, okay? And this is by definition equal to F star of the definition of mu and j, which is this, 1 over n, the sum of Fi star mu 0, I equals 0 to n minus 1. And this F star, it's easy to check that this can come inside, so this is just equal to 1 over n, the sum I equals 0 to n minus 1 of F I plus 1 star of mu 0. And then I'm going to write this as this should be 1 over nj, right? 1 over nj, because we're taking this subsequence nj. And this is 1 over nj. And then I can write this, let me write this here. Let me write this first as 1 over n times the sum from I equals 0 to n minus 1 of that I star mu 0. And then I need to add and subtract as usual, right? The terms that I've not included in here. So this is Now when I equals 0, this is just mu 0, but here I do no longer have that, so I need to add mu 0. Sorry, I need to subtract mu 0 from this, because mu 0 is no longer included in this, because when I equals 0 I have f star mu 0, so I need to subtract and I need to add the last term that I get here, and the last term here is when nj minus 1 plus 1 is f nj star of mu 0. Okay? So just add and subtract these additional terms. So if you check, if you write out the sum minus mu 0 plus this, you see that you get exactly this. Okay? And this I can write as 1 over n, the sum I equals 0 to n minus 1 of I star mu 0 plus, let me write it like this, 1 over n f nj mu 0 minus mu 0. And what is this? This is just 1 over n sum. This is exactly this term here, right? So this is just exactly mu nj. Sorry, these are all nj's. Yeah, nj's. And so here this is exactly equal to mu nj plus 1 over nj f nj mu 0 minus mu 0. So what happens here was nj goes to infinity, right? We have that mu nj converges to mu n, to mu by definition, right? And what does this converge to?
0.
0, right? Because the total mass of these is just bounded by 1, so the contribution of this to the whole measure is going to 0. So this is just converging to mu. So how does this complete the proof?
The left-hand side converges to f.
Exactly, right? So by continuity, so we prove that, so we have that mu of nj converges to mu, f star of mu nj also converges to mu, okay? But by continuity of f star, but by continuity of f star, we also have that f star of mu nj converges to f star of mu. Right? So we know by continuity that f star of mu nj converges to f star of mu, but we've shown by this calculation that f star of mu nj converges to mu, so this implies that f star mu is equal to mu, which says that mu is invariant. Okay? Okay, so I think this completes this first chapter on invariant measures. We've defined invariant measures. We've motivated them by the Poincare recurrence theorem and the first part of Birkhoff's theorem, right, that says that the limits exist. And we've shown that in very general situations, when X is compact and F is continuous, at least invariant measures exist. So it kind of makes sense to think that having an invariant measure is a relatively natural condition in a dynamical system. Although we've also seen systems that don't have invariant measures, so it's not always useful. But if by Poincare recurrence thing, if you don't have an invariant measure, then you don't have any recurrence, right? So in some sense, if you don't have an invariant measure, the dynamics is not very interesting anyway. Okay. So in the last 20 minutes or so, let me start introducing the next chapter, which is, as I said before, we would like to be a little bit more precise in Birkhoff's theorem, and for this we need to introduce another notion for measures. So let me call this section ergodic measures. So this first one was invariant measures. And let me write the definition here. Definition is that a probability. So again, we always have our map, okay, from a metric space to itself, measurable map, and we say that mu, and mu is some probability measure. So mu is ergodic with respect to f. So ergodicity, again, just like invariance, it's a relationship between the measure and the map. And if now it's a little bit more subtle, the definition of ergodicity, so you need to be a bit more careful. If for all a such that f minus 1 of a equals a, we have that mu of a equals 0 or mu of a equals 1. So we will give several examples and think about what this means exactly. Let me actually first give an example of a non-ergodic measure, because that way we can get a clearer idea. Example. So let me draw this map here. 0, 1, 0, 1. And and this map is like this. This is 1/2, this is 1/4, this is 3/4. And these are piecewise affine map. Okay? So, observation 1, Lebesgue measure is invariant. Why is it invariant? Lebesgue measure, can you see? Yeah? So, what is the slope here? What is the slope of these graphs? The slope here? -2, the slope here? 2, slope -2. Okay? So if you take an interval here, A, and you look at the pre-images, it will have 2 components, each one half the size, just like the arguments we did in the other maps, right? And if you have here an interval and you take its pre-image, it will also have 2 components exactly half the size. Okay? So Lebesgue measure is invariant. But it's not ergodic. Why is it not ergodic? So what this means is that, so the negation of this statement is that there exists a set, so the map F, the measure mu is not ergodic if there exists a set where f minus 1 of a equals a, which has measures strictly between 0 and 1.
1/2 to 1.
Exactly. Okay? So in fact these two sets, 0 to 1/2 or 1/2 to 1, both of them satisfy this condition, right? If you take the pre-image of 0 to 1/2, it is exactly 0 to 1/2. And the measure of this is 1/2. Okay? So this contradicts, this shows that this measure is not ergodic, and the same here. Okay? And what this means really in practical terms is that if you start inside here, then you stay, if you stay inside the interval 0, 1/2, here, sorry, 0, 1/2, I should write here, then you stay inside 0, 1/2, and all the pre-images of every point in here is in 0, 1/2. So really, this interval 0, 1/2 is its own dynamical system that is completely separate from the interval 1/2, 1. Everything that starts in here stays in here both in forward and backward time. Okay, it's the same here. And this is a general, but not ergodic. So let me write this, but not ergodic. This is a general fact about this. This condition here is more powerful than it seems at first sight. So let me make just some remarks about this. Remarks. Notice that f minus 1 of a equals a implies various things. So it implies, first of all, that f of a equals a. Do you agree with that? Yeah, this is just a set theoretic thing, because if a point, if every point, every pre-image belongs to A, then taking the pre-images on both sides, you get that f, taking the images on both sides, so f of f minus 1 of A will be equal to f of A, which is exactly this. Okay? So backward invariance, whereas the converse is not true, right? Can you see that the converse is not true? Can you give me an example where if a set is forward invariant, it is not necessarily backward invariant?
Y equals x squared from f of 0 to 1.
Yes.
Equal to 0, 1.
Exactly.
If f versus 0, 1 is minus 1 to 1.
Any map that is not invertible, one point may have two pre-images, right? So for example, if you take a fixed point, right, then the image of the fixed point is the fixed point, but the pre-image of the fixed point contains the fixed point, but it may contain another point, right? So the fixed point itself will satisfy this condition, but may not necessarily satisfy this condition, if the map is not invertible. Right? If the map is invertible, then they're exactly equivalent, these two conditions. Okay? But perhaps most importantly is that it also implies that the same property holds for the complement of A. And this follows immediately by these two, right? So basically what we're saying is that we have our map f x to x, and then we have the set A, which is both backward and forward invariant, right? So if you take any point in A, then all its forward images will be in A, and all its backward images will be in A. And therefore, clearly, if you take a point in the complement, it will also have to stay in the complement in forward and backward time. Because if you take a point in the complement and its image at some point belongs to A, then that means that some pre-image of A belongs to the complement, which contradicts that. Okay? So the key, the most important implication is this one, in some sense. And so what this is, because of course this also means by the same argument that f of AC equals C, right? So what we're saying, so f minus 1 of A equals A says that x is equal to A union A complement, where A and A complement are fully invariant, fully forward and backward invariant sets. So this is the way to think about every time that you see this condition here. It is saying really that you're decomposing your space into the set A and its complement, and in some sense they become two independent sub-dynamical systems. Okay, so you have a dynamical system. If you look at the point A, you can study all the dynamics in forward and backward time just staying inside A, and the same for the complement of A. Alright? So the ergodicity says that if you have any set like this, then either A or its complement, either A has full measure or its complement has full measure, right? The fact that A has zero measure. So what it's saying is that you cannot decompose your system into two dynamical systems where this measure gives positive weight to both of these dynamical systems, right? In this case, where we have non-ergodicity, we have that Lebesgue measure, we have two sets, two non-trivial sets, A and A complement, if you want, and the measure gives positive measure to both of them. So in some sense, this measure is really seeing two different dynamical systems, right? It's saying one dynamical system is happening in here. If you're in here, you stay in here forever. If you're here, you're staying in here forever. Okay? So of course, this particular system may have many measures. Some of them are invariant, some of them are ergodic, and some of them are not ergodic. For example, here there's a fixed point, right? And so we can define the Dirac delta on the fixed point. So, for example, if f of p equals p, okay, then Dirac delta on p, is it ergodic or not ergodic? It's ergodic. In this case, it's kind of ergodic in a trivial sense because, again, every set has measure 0, 1 in this case, right? But in particular, delta p is ergodic. Okay? So, in this system, if you take the Dirac delta point on Dirac delta measure on p, then this whole dynamical system, then this measure is ergodic with respect to this dynamical system. So it means, as far as this measure is concerned, you cannot decompose the system into different parts. Okay? With the example of the Dirac measure is kind of trivial, because of course all you're seeing in that measure is this fixed point. You don't see anything else. So of course you cannot decompose it. But that is the concept of an ergodic measure, is that as far as that measure is concerned, once you choose your measure, that's the measure that you choose to look at your system, and then you say, with respect to this measure, can I decompose my system? Okay. So, what about if we take a combination of these measures? Like, so suppose, for example, that I take, suppose mu is equal to 1/2 of Lebesgue plus delta p for this map. So this is a probability measure, okay? It means that for any set, right, so mu of A is equal to 1/2 Lebesgue measure of A plus 1/2 the Dirac delta p measure of A. It's a probability measure, it's fine. Is this measure invariant for that map?
No. Can take again 0, 1, 1.
Is it invariant?
We can take T.
Invariant. It's invariant because, as we saw before, any linear combination of invariant measures is invariant. Okay, so there's a linear combination. We just showed that these two are both invariant measures for the system. We take a linear combination, so it's invariant. Okay? Is it ergodic? No, it's not ergodic. Because you can take, you can take the same Same thing we did before, actually. You can take this, so you can decompose it into various ways to show it's not ergodic. So the main motivation behind ergodicity, so just a small remark is that the definition of ergodicity does not require the measure to be invariant, right? The definition is for any measure. But in practice, we will be interested in measures that are invariant and ergodic both. But the definition does not need, so almost always, also in the literature, almost always when you see referred to an ergodic measure, it means ergodic and invariant. It's kind of implicit that we're talking about invariant measures. But the definition does not, and in fact, later on in the course, we're going to look at some measures that are ergodic even without being invariant, and they will be relevant for what to do. So the most important reason to introduce the notion of ergodicity is Birkhoff's ergodic theorem, which is the second part of the theorem the full version in some sense of the theorem that I wrote the other day. Birkhoff, again, this is from the 1930s, I think 1931, that says that, okay, so we have fx to x. In this case, x just needs to be a measure space, f just needs to be a measurable function, and we have mu is f invariant and f ergodic, or just invariant and ergodic probability measure. And then for all phi in L1 of mu, we have that phi f, a limit n to infinity of 1 over n, the sum of phi composing f on x. So remember what this quantity is? Yeah, we looked at it last time. So we have our system f, x to x, then we have our function phi, right? And then we look at the orbit, we have point x, okay, and we have all the iterates of x, and we evaluate phi along the orbit of x, and we take the average value of phi, right? And remember that I stated before that as long as the measure is invariant, it implies that this limit exists. So this should be a definition. This limit exists, and if the measure is now ergodic, we have a significant amount of additional information, which is we know what this converges to, and this converges exactly to the integral of phi dm. For all phi and mu almost every x, this converges to the integral of mu. So I think that again, I'm going to give the same example as before as an immediate corollary. If phi is equal to the characteristic function of some set A, then this is where it's really kind of striking, okay? Remember, we said if phi is a characteristic function, this is just counting the average number of times that it belongs to A, right? So this is a some set A, so you're looking at the average number of times, so this gives 1 over n times the cardinality of the indexes such that fi of x belongs to A. Right? This is exactly this. Okay? And this limit, this converges to the integral of the characteristic function A d mu, which is the measure of A.
I think this is an integral phi, and this is a number, I mean real number, but there is some in this part is function.
Excuse me?
this integral is equal to, it doesn't depend to x.
Well, that's exactly the main point of the theorem. This is exactly the remarkable point of the theorem, because as long as you say, using only the invariants, we know that this limit exists. Okay? The remarkable fact of this is that if the measure is ergodic, then the limit does not depend on x, and it is exactly equal to the average value of phi. But, don't forget, we'll look at some examples. It does not depend on x in the sense that it is the same and it's equal to this for mu almost every x. It can never be true for every x, right? Because if you look at this corollary here, then if there's a fixed point here, it will never enter A, which there may be. Okay? So it depends on the measure that we've chosen. So both the measure of A, this is a key point which I will discuss a little bit more. So the measure enters in two different ways. In this is the intuitive understanding of this. This is of course more general, but the intuitive understanding is that the measure enters in that it's the measure of A. For example, if we take the Dirac delta, if we have a fixed point here, and our measure is the Dirac delta on the fixed point, then this set A here will have zero measure, and then almost every point will enter 0 times in here, but of course with respect to the Dirac delta measure, almost every point is just the fixed point itself. Right? If you take, let me say this a little bit more slowly because it's very important. So I want to discuss the limitations, both the powers and the limitations of this theorem, because this is probably one of the most important and significant theorems in dynamical systems and ergodic theory, but it has some limitations, right? So the power is what you've emphasized, which is the fact that this limit does not depend on x. Okay, clearly, and the fact that this limit is very explicitly given by this. So what this means is that in some sense, almost every orbit is uniformly distributed in your space. Right? That's what this means. Because the average value of phi is saying what is the average value. If phi is some function like this, right? The average value is just the average value of phi, is the integral of phi is this. And so if you look at a point that moves in space, and in some sense it's like saying that the orbit is uniformly distributed according to this measure, right? It spends a certain amount of time here, a certain amount of time here, exactly in such a way that the average, this is sometimes called the time averages of phi, and this is sometimes called the space average of phi. Because these are the time averages along the orbit of x, and this is the space average because it's just the average in space as measured with this. So sometimes this is informally talked about as the Birkhoff ergodic theorem says that for almost every point the time averages converge to the space average. Okay, that's how it is. So let's look at some examples. Now, so first of all, one of the things that counterbalances the power of this theorem is that it is very difficult to prove the ergodicity of measures. Okay, in some sense that's going to be the theme of the rest of the course from now on. The problem is that you need to prove, there's two problems. First of all, even if you get an ergodic measure, then as we shall see, there's some limitations. But anyway, it's very difficult to prove that measures are ergodic. Okay? And in some sense, the history of the so-called differentiable ergodic theory, or ergodic theory of dynamical systems, which is kind of my area, is really more or less one of the core underlying themes is how to prove that certain measures are ergodic. Okay, it's one of the biggest challenges. So this is what we're going to develop, some techniques to prove ergodicity, and we're going to prove some examples of ergodic, where we have some ergodic probability measures. First, let me just in 5 minutes give some example. So what we're going to prove, okay, let's take our favorite map fx equals 10x mod 1, which we have seen before. Okay, so we have that 10x. We know what the graph looks like. So this is 0, 1. Okay, so we will discuss this more in detail in the next lecture, but for the moment I just want to point out, so it is a theorem which we will prove that Lebesgue measure is invariant and ergodic. So invariance we've already shown, invariance is very simple, ergodicity is non-trivial to show. But let's just talk for a few minutes about the consequence of ergodicity. In terms of this, for example. Okay. What does this mean? This means that if I take the interval 0.1 to 0.2, almost every point will visit this interval. Okay, but that we knew already just from symbolic dynamics, right? Because every time you have in your decimal expansion, you have the digit 2, then you will visit this interval, the digit 1, sorry, you will visit this interval. But now, using the fact that Lebesgue measure is invariant and ergodic, and using Birkhoff's ergodic theorem, we know how often we will visit this interval. How often will we visit this interval? 1/10 of the time. Okay? And what does that imply about the decimal expansion of these points? Every time it visits this interval is because the digit 1 appears in the decimal expansion, remember? Right? So it means that if you look at the decimal expansion of the point, the digit 1 will occur 1/10 of the time. Yeah? Asymptotically. Because this is a limit, right? So you might have a number whose decimal expansion, the digit 1 does not appear for the first 1 million digits. That doesn't matter, okay? But in the limit, when you look at the first 1 million, billion, okay, and you count how many ones there are, in the limit, the proportion of 1 converges to 1/10 exactly. For Lebesgue, almost every point. Right? This is a direct consequence of Birkhoff's ergodic theorem. So this is a very nice corollary, basically in number theory that has nothing to do with dynamics, but it's an immediate corollary of Birkhoff's ergodic theorem. And the same for all the other digits. So in fact, what this theorem says, the corollary of Birkhoff's ergodic theorem is that Lebesgue, almost every point, if you look at the decimal expansion, asymptotically each digit occurs 1/10 of the time. That's what it implies. But now let me just ask you one more question. Now here, we know that there is a fixed point. There are many fixed points. For example, here, there is the fixed point, say 0.8 recurring. Okay, let's call this P. Okay. So if we apply Birkhoff's, so both the Lebesgue measures invariant and ergodic, okay, but also delta P, where P is equal to 0.8, is invariant and ergodic. Right? So we can apply Birkhoff's ergodic theorem also to this measure. Okay? So by Birkhoff's ergodic theorem, we have that if this is our set A is equal to the set 0, 1, 0, 2, okay? By Birkhoff's ergodic theorem, we have that the frequency of visits, we have that, well, let me write it like this: 1 over n, the integral of phi composed with fi of x converges to the integral of phi with respect to the measure delta p. Right? But we also have 1 over n of the phi composed with fi over x converges to the integral of phi d Lebesgue. So if a system has several invariant ergodic measures, as is the case, then we have, like in these particular examples, Birkhoff's ergodic theorem gives us two different limits to which this sequence converges. So how is that possible? Because in general, the integral of phi with respect to the Dirac delta measure will be completely different from the integral of phi with respect to the Lebesgue measure.
Yeah, but mu of
Because one, the first one is maybe say that it converges to exactly.
yeah, but the second one is Lebesgue almost everywhere, and the first one is Dirac delta.
Exactly. Okay, I'm just trying to emphasize what I already emphasized, but to re-emphasize it again, is that the conclusion holds for these points, right? So in this case, this is true for delta p almost every x, and this holds for Lebesgue almost every x. What does delta p, or what does almost every x mean? Mu almost every x, what does it mean?
Measure of all the points are zero.
Exactly. So it means that there is a set of zero measure for which we don't know. Okay? So what this is saying is that there is a set for which this may not be true, but this set has zero Lebesgue measure. Okay? And this statement says that there is a set for which this may not be true, but this set has zero measure for delta p. And of course the two things are not contradictory because everything has zero measure. If you just remove the whole interval minus this point has zero measure. Right? So in particular there's no contradiction between these two because this set of points that has full Lebesgue measure has zero measure for delta p. And the point P, which has full measure for this, has zero measure with respect to Lebesgue. So these are statements that are talking about different points. So they're both correct. So for any measure, it's saying that the limit does not depend on x, but it only holds for mu almost every x. Okay, so this is the independence of x, but it's independent with respect to a particular measure. Okay, so it's a very, very powerful theorem, but it needs to be, you need to really understand that it is, in general, you may have lots of invariant ergodic measures. Okay, so depending on which invariant ergodic measure you choose, you get different limits here, but these limits only apply to almost every point with respect to that measure that you've chosen. And these are all disjoint sets of points. Okay, so I think that's good for today. Thank you.